Hello, Spark fans, and welcome back to Advancing Spark, where today we've got a bit of an interesting one. So we saw in some of the release notes a little while back, we had a load of H3 functions released into Spark. And what is that? Well, we're mentioning it's geospatial, and it's useful for looking at giant maps and doing data analysis over it, but we didn't really go too much into it. So today we've got some of the guys from Databricks over to give us a bit of a tour about Mosaic, one of the open source projects in Databricks Labs, about how to really get the most out of H3 and geospatial, what it's for, and to give us a bit of a guided tour. As always, don't forget to like and subscribe if you're new around here. Let us know down in the comments what you're currently doing for geospatial, and if you've had a chance to get any of the H3 functions into action. So without further ado, let me introduce Milos. Hello, welcome to the channel.
Hello.
How's it going? Do you want to tell us a bit about yourself, about your role, about what you do?
Sure thing. So, hi, my name is Milos, or Milos, depends on the transcription. I lost a few accents traveling around. A bit of another geospatial use case there for you. But yeah, I'm a senior solution architect working with our public sector team in EMEA. And I'm one of the geospatial SMEs for Databricks. I cover accounts when it comes to geospatial on a somewhat global level. So I've talked with a few people in US, EMEA, Australia, all the places.
So it's fair to say you know what you're talking about when it comes to geospatial.
On Mondays, yes. On other days, depends.
All right, cool. So you've given me a few slides we're going to walk through just to kind of tell the story. And I guess the aim of today is to kind of introduce people to the topic and why we're doing it and what you can get out of it and kind of set that foundation, right?
Yeah, I believe so. So the idea is to, talk a little bit about why geospatial data is important, what it can bring to your use cases. My background also comes a little bit from data science and data engineering, so I'll try to tie in a few concepts so people understand, how I came to work with geospatial and why I stick with it. And then we'll walk through a little bit of what came into Databricks Photon Engine, what Mosaic is as a framework that you already mentioned that uses all of those concepts under the hood, and a couple of use cases that are interesting.
Sounds good. So I'll be the slide person for today. So just let me know when I need to change slides, and I'll be clicking away. But yeah.
Yeah. Well, so on the screen you pretty much have the most common quote, and I do believe in the industry there is a little bit of a battle who first said it. I'm going to go with Ordnance Survey did because I'm based in London and I have my bias there, but everything happens somewhere, and it's probably the most quoted sentence. It's very short, so it's easy actually to slam it in anything you write, but it really does. Everything does happen somewhere, and that makes geospatial data everywhere. And one of the things that I like to open up when we have these discussions is we use data science and data engineering and data in general to model the real world, but the real world pretty much is located somewhere. Any event, any data row has that location component, and we then choose to capture it or not. So there is a wide amount of information that we may lose if we decide to remove it. So today we're talking about why not to remove it and how you can actually yield more value out of your data if you keep it there. And we have a few examples to just describe what we mean when we say geospatial data sources. So if I start with anything that has latitude and longitude, it's pretty much a coordinate, and it's pretty much a geospatial point data. Now, that's on a really simplistic end, and you can even encounter these things in like CSV and flat files. It's fairly easy to get a hold of something like that. In a real world example, that would be maybe your point of sale. So, I have spent some money in this store. That's the point location of the store. But then if you start expanding on that, comes vector data. And these are like your shapes, your postcode areas, your LSOAs, MSOAs if you're in UK, your state boundaries if you're in US, your road network. It gets anything that can be represented by a line or a closed line or a set of closed lines. And finally, we have raster, which is, well, not finally, we have LiDAR as well. But raster is your, I like to call it scientific imagery for people that are not necessarily familiar with it. It is an image, but it can have many layers. They're usually called bands, and they can contain information about many things. So from your wind speed to your exposure to sunlight, to your vegetation index, your soil type. You can have multiple layers of soil, and new satellites, for instance, that also generate that raster data. So satellite imagery is a satellite data. They can go to a resolution of, I believe, 30 centimeter by 30 centimeter, which is a larger dinner plate. So we can capture the world very, very in a very, very detailed manner.
That is an insane amount of data.
And when we're going in the most complex way of capturing data from the volumetrics perspective, it's probably going to be a LiDAR. It's a combination of a laser and radar for the ones that are not familiar with the LiDAR term. But basically, you see your Google cars going around. They usually have one of those attached, and they can scan the 3D features of the space around them. It basically shoots the laser very, very frequently, and it captures a lot of refraction, and those are the points, how distant they are.
That's pretty damn cool.
Yeah, it's pretty scientific in that sense. But that can actually help you build it.
I think a lot of people like me are coming from the very easy vector side of things, So when I've done any kind of geospatial, I'm using like Power BI or data viz tools. You can throw some lat and long, throw it at some geometric shapes if you're being very, very fancy. And I think that's about as far as the majority of people get. So it's really interesting to see these deeper, more advanced use cases for this stuff.
Yeah, if we go with the Pareto optimality, probably by raster, we have covered 80% of people. There are use cases, and we just want to, give them a proper shout. But yeah, this is all of the data that you can actually consider geospatial. And as you can see, the complexity increases quite quickly, but there is a lot of valuable use cases that these can be attached to. We can go, speaking of use cases, I think we can go to the next slide there. And given that breadth of different use cases you can attach the data to, we do really believe that Lakehouse is the right place to operate with geospatial data for two main reasons. Like the data comes in various different formats. So we're talking about dozens and dozens of different formats, and it comes in different volumes, and then finally it comes in different typology. So we have structured, semi-structured, and unstructured data. We talked a little bit about imagery. They are built-in structures, but usually when you throw this as a naive Python script, you'll actually perceive it as just bytes. So there is a little bit of, how do we make sense out of it? And here you can actually see how the data flows. So I mentioned transactional data, so it can have positions. Demographic usually comes with location data, news articles, where did they happen in the world, transportation data, ESG data is a very geospatial thing. Sustainability is a location problem. I know it's becoming more and more evident that is the case, and climate data tends to come as a geospatial asset. So a lot of toughest problems today are attached to that. And once you got all of that data, you obviously want to do something with it. So you want that richness of tools. So it's not just BI, it's also spatial SQL, it's also AI, it's ML. All of that is available as part of the Lakehouse ecosystem, and we are building solution accelerators that can actually get you end-to-end for certain use cases, and we'll touch a bit about them as well later. But they can get you end-to-end for through use case. And here we list just a couple of exemplary industries. But pretty much any sector will benefit from geospatial because it's a foundation, it's a horizontal thing.
Yeah, massively. I mean, so the kind of work we've done with various clients, we keep coming across people who are, oh yeah, we've got this data, and we're like, well, that's a geospatial, but you can do loads with that data. But often it's kind of forgotten about. People who have managing vehicle fleets, and their various different vehicles is kicking out just telemetry constantly about the telematics of where things are. You can use that to do geospatial. Just tons and tons of this stuff.
That's a very good example. IoT data in general is very spatial in that sense. And, if you tie it back to energy, then also like you have a vast amount of telemetry data being sent through the sensors, and they have a location, and it doesn't matter where on the network things occur. So if we go to to next slide, we covered a little bit about the richness. So we talked about two things that we're going to cover in more detail, which is the native support on Databricks product, what we call here as a geo product. This is H3. You mentioned it a little bit. Was recently announced. We have H3 capability natively available as a part of Photon Engine. And that's really exciting because it can bring you manifold performance boost and simplification of usage than if you had to hack those by yourself using H3 library and then building user-defined function, which tend to not be the best idea in for large processing. And
I spend most of my time telling people they're not allowed to do UDFs. Just no.
Yeah. Sometimes you can't avoid them, but yeah, usually they come at a cost, and we're not always happy to pay it. Yeah, that's true. And yeah, second thing that we may want to cover, what we will cover, is the Mosaic, which is a Databricks Labs project that focuses as well on geospatial and uses that H3 functionality under the hood. So if you've already been using Mosaic before H3 was announced, you're good to go. The same thing will work with H3 under the hood. We have rewired everything. So if Photon is available on your workspace and your cluster, we will use those capabilities as part of Mosaic. If they are not, we will fall back for the current versions of Mosaic onto what was there inside. Now, but the ecosystem is much wider, and you have, this is pretty much pick your adventure or choose your class type of situation. All of these tools are integratable with Lakehouse. So this is not like you have to abandon any of this. It's just some of them are more direct, which is native support and in easier queues. Others will need a little bit of a holding hand maybe, and then some tutorials to get through. It's we're talking about large scalable problems, so just trying to manage the expectation of people is not just snap your fingers and all of a sudden everything always flies. I think from that perspective, if we go the next slide, we do have a little bit of a navigate through the ecosystem, which helps with the understanding. When you are looking at your data and you identify vector, raster, or point cloud data, how do you choose your tooling? So we do have, as I said, some solution accelerators. They are attached to different industries and specific use cases. So if you find your use case already implemented, they're all available as a part of Mosaic repository on GitHub. So it's an open code. Feel free, pick it up, try it yourself. If something does not work, give us a shout. We'll help you fix it. It's all been battle tested, and all of the use cases have been used by other customers in production. But there are always some details that may require a little bit of a nice touch.
But you kind of assume that from solution accelerators anyway. They're there to get you started on the journey, to show you a good example of using it, but you've got to tweak it to exactly what you're doing.
Exactly. The idea is to shorten the overall time to value rather than actually say it always magically works. So the idea is we captured as much as we could from the industry about the use case, but then there are some details that every organization has uniqueness to it that we need to account for. Now, you may have some custom specific geospatial workloads. We'll try to work with you if we can remap them to an industry accelerators, or we may help you build it from scratch. Now, depending on definition of the problem, you may go into one of these three paths. Either you're going to use native features as part of the Photon. You can actually address your problems through direct spatial SQL usage. You may need something more advanced, maybe using Mosaic or Spark, and or one of our integrations that we have. There were a couple of blogs recently being announced. There is an integration with Carto. There is an integration with H3. Some others may be coming along the way. So, do stay tuned for these. It's an exciting field. But obviously, all of those feed into all of your other use cases that you already have in Databricks. So it's more of a augmentation discussion here. How do we actually get that value squeezed out of the geospatial data? So I think I already kind of spent a lot of effort from the next slide talking about it, but just some specifics. So from Databricks Runtime 11.2 onwards, we do have H3 built-in functionalities. What H3 is a grid system, and it brings some scalability concepts into the mix. And on the next slide, I'll walk you through the actual details of H3. But here we just also revisit all of the use cases that we kind of mentioned. So, thinking from human mobility to precision agriculture, it covers the whole breadth of industries. And I'd be really surprised if you came and said, my industry doesn't have any geospatial data. I'm opening up a challenge, so put it in the comments. If you have the industry that can prove me wrong, I'd be really happy to hear about it. But yeah, on the next slide then, please. Let's spend a couple of minutes on what H3 is and why we brought it into Spark and why is this the first thing that we implemented in Photon around geospatial. So one of the interesting things, annoying things even, but good, interesting, annoying kind of makes it it's a difficulty of processing geospatial data is it actually has skew in some hidden places. So I'm not talking your partition skew. That's there too. You're not going to avoid that. Municipal areas versus rural areas, there is a skew. So, but we know how to handle those. There are skew hints. There are all sorts of tooling that we already developed. But we have within the row type of skew inside of the data. Think of road segments, for instance. Not every road segment has the same complexity. If you have a curvature, that adds a lot of points. If you have a lot of turns, that also adds amount of data captured. So a straight line is not the same as a curved line, is not the same as a meandering line, is not the same as a broken line. So that means that not every row is equal to another row. And that's a problem because that's another source of skew. So your threads are not going to spend the same amount of compute on all of the rows in the data. And then it kind of actually creates a very, sub-partition skew. So grids are very good because they can help you split features into partial features. So you have a grid that covers the whole Earth in a hexagon tiles, and they basically form an envelope around the Earth, and they have many resolutions, which you see here in the central 3 images. So it can go at a different level of detail, and now that basically gives a rasterization of the world. And if you have a line going through all of these cells, you can clip it and actually say, all of these multiple lines form the parent feature, but I can process them in parallel because spatially the context is contained.
A grid is a grid. Yeah,
grid is a grid.
Makes a lot of sense.
And that then can help you also represent some very complicated use cases, like the one there that you see in the center on the right hand side with that red and yellow lines. That's actually an airplane holding pattern detection, and you can represent a complicated path in the space using these cells. And the red area are the revisited one, and when we see the red, we actually know there was a holding pattern. The airplane didn't go straight to the runway. So it's really a good way to abstract the world, and it solves for a lot of those complexities of the geospatial data. So if we go
for me, this is the slide that actually made it make a lot more sense what H3 was actually about, because I'd seen the release notes and I'd seen, hey, you've got all these new functions, and I'm like, okay, is it just a load of new algorithms on top of other geospatial stuff? But actually getting the context of it's a specific way of modeling it, built for scale, built for easy distribution so you can parallelize over it with this view the world in a slightly easier, like sort of stylized sense so that you can break it up, makes a lot of sense to me.
And one other thing, actually, it's also a matter of interoperability, to be honest, because it's a global grid index. It has been adopted by some other players in the market. So Esri does have in some of their product support for H3. Carta does have it as well. We've seen it in GeoServer as an open source alternative. So it's not just Databricks unique view onto the world. It's something that will help tools integrate. And that's really important because we can't assume that you only have one thing in your wider ecosystem.
Yeah, of course.
Enterprise architecture is a wider picture.
Again, common standards is fantastic for the open source market, right? Makes sense.
Absolutely. And then if we go to the next slide, please. As we said, so because of all of this goodness coming from H3, we decided to support it natively in Photon. As I said, from the Databricks Runtime 11.2, this is available. And why is it great? Well, on average, it gives you about 20-30% faster execution than what you would get even like in native support on Spark in Java. So this is beyond so UDF's slow, native Java supporting Catalyst fast, Photon think faster. And average is actually a little bit of misleading here, and you'll see that on the next slide. So if we go just to the next one where all the goodness is, it actually in some cases it's almost near 10 times faster execution. If we take, for instance, H3 distance between two cells, And that's a great thing about this grid, actually. You can use it as a proxy to distance. And Uber originally developed this to actually streamline the routing and approximate the distance travel through the indices, because they are so well displaced in the space. So you can actually approximate distance fairly well using the grids alone without actually doing the distance function. So we have a few families of these functionalities implemented. You'll see here like traversal. What is traversal? So when I am in one of these grids, there are functions that can actually give me a relation to the nearest ones. So we call those k-rings or disks. So you can have them, what is one cell away from me? What is two cells away from me? That can be really interesting for use cases like, for this house, give me nearest schools.
Yeah.
It's really give you that vicinity and proximity. Then distances, I already touched about H3 distance. So you can measure the distance between different two cells on a straight line that traverses the grid. So you can approximate the time to travel between two locations very quickly. And that can be the first way to trim down and size the problems for more advanced compute that will take a lot of more resources.
So it's kind of like between these 2 points, we need to traverse through 20 cells to get there, and we know the rough distance of cell for this resolution, so you can approximate from there, that kind of thing.
Yeah, that gives you like the straight line travel, but then you can know if the straight line travel is the absolute minimum of what you can do, then anything actually Manhattan-wise is longer. You know, you don't really need to consider some destinations if they're too far based on a threshold. So it can really help you, push down filters and similar.
Yeah, interesting. Cool.
And a lot more coming there. So you can please visit the documentation and see a full set of these expression. I don't necessarily want to taxatively go through all 30 of them. We'll probably be here until tomorrow.
Yeah, we're not going to read the docs out. We'll move on.
And I think cherry on top of all of this, and one thing that I did not cover when I was introducing the grid, but I think this is the right place to. It fits really like a hand in a glove with Delta Lake principles. So the H3 indices are what we call the space filling curve. And now I know in some previous videos you talked about Z ordering and what it can bring. Z ordering itself is a space filling curve, and what that means is it arranges the data on the disk in a way that we can efficiently skip large portions of the data. H3 is built as a space filling curve, so actually if you Z order based on your H3 indices, you achieve the same effect. So data that's close spatially to each other, it's put in the same part of the storage, and the data that's far away, it's put far away. What that gives you is when you're querying, you tend to have the first principle of geography. Things that are close to each other tend to relate. Things that are far from each other tend to not relate. So most of the queries tend to be very located. So it fits. It really works well. So do give it a go. It can bring a lot of performance benefits. And you just really same principles, just finally clicking one to another.
So is that general kind of part of your general performance advice if people are building anything on H3, they should use Delta and Z order by the H3 indices? It's just kind of a best practice guideline.
It is. And because Z ordering allows you to have multiple columns, I would say if your queries are very spatial in nature, start the first column being H3 and then followed by your filter keys or join keys. Probably join keys and filter keys, but bear in mind, Hilbert curves do tend to stop performing after fifth column, so don't just smack everything you think there. Be selective a little bit. But this is more of a beyond geo tip.
That's fair. Cool. All right. Yeah, sounds good.
And the next slide will cover a little bit on how you can then represent. So H3 can be used to represent the complex shape in a few different manners. So one naive way is don't use it, which is the far right here, geometry centric. You have very little spatial data, a few hundred rows, maybe a couple of thousand rows. You know what? Use GeoPandas. They're available on your notebooks. You don't really need to spin up a large amount of compute. You can use traditional functionality. But then let's talk about proper scalable problems. You have two options. Like you go H3 centric, and you have these concepts of polyfill, which will actually represent your polygons or your closed shapes. as a set of indices, but it will have a little bit of a false positive and false negative areas around the edges, because it's actually trying to select a set of pixels or cells contained within the shape. That's good. It does lose a little bit of expressive power, but it's really fast. It's super snappy. Now, the alternative to that is when you say, okay, hold on, I don't want to lose any of my data. I actually have defined these areas because I need them that way. You can use a hybrid approach, and that's what we developed in that framework called Mosaic. It will use H3 to tessellate rather than fill. It will split any cell that covers multiple geometries. It will split into subsections. Okay. So you actually get the full level of detail and localized geometries. So it works with any type of shape, lines, polygons, multi-polygons.
Essentially, if there's any edges that was made up of tessellating hexagons, you just kind of draw the actual line over it and then be able to split it, but you can still scale across those things.
Exactly. So you then, in that case, you will keep the H3 ID, which is a long value or a string. We do advise long values. You get much better performance because all of the optimizations works better with numerical data than strings, but both are supported. But then you get that ID, and then you get the well-known binary representing that little segment. So you can actually have that duality, and it works really, really nice.
Very cool.
And then if we go to the next one, so we also have inside, we have recently released a blog. We'll provide a link in the description around the support and all of these approaches, everything we're covering today. But we have given you a little bit of I will call this instead of a decision tree, I'll call it a decision map, because we're in geospatial world, right? It's how do you navigate all of this, how you choose your tool. So, depending on whether you're preferring scalability or accuracy, whether you prefer, you have medium or small scale, all of those things will come into play, and we can actually help you choose what to use, which out of those three approaches. We have provided it in a blog, so it's always there as a cheat sheet. But if you get stuck, do phone us up, and we'll help you unblock and go forward.
Now, and I'll put a link to that blog down in the description below for people kind of who want to go and have a look.
Absolutely. And how does that feed then into your medallion structure and your Lakehouse? That's on the next slide. Everything remains the same from that perspective. The thing that changes is the number of formats. So it just the problem got expanded. We have more formats to handle, but then the data still lands in bronze. And then as part of your silver, there is one consideration that you want to take into account: index your data, use H3, make sure that you get that Z order in place, make sure that you can get that file skipping, and then serve your data. Serve selected, curated data in your gold layers. We do have, as part of, again, Mosaic ability to do ST is valid, so you can check for self-intersecting geometries and few common problems that could occur there. And then when you serve it, you can use it for analytics inside of the Lakehouse, or you can use it for enterprise-grade UI serving, like through integrations with Carto, Tableau, Esri, open source things like Kepler or GeoServer.
Which again makes sense why it just fits in a Lakehouse pen. If you can treat it like any other data, you land the data, you do some validation to the data, you shape and curate the data, and then you serve it out. It's no different to any other data type. It's just we've now got some more useful functions and indexes and things we can do on the top to make it even better in that style.
Absolutely. So we do have tailored capabilities for geospatial data, but in the end, it's data. So you'll benefit from putting it in Lakehouse from a few other things that are not geospatial specific. So we're talking about lineage. It's been announced recently for Unity Catalog as a GA. So you'll get your lineage out of the box. You'll get your delta sharing capability. So we're going to think about geospatial data as a product. There is a blog coming soon, probably early in the next year, around designing geospatial data as products. And obviously, if you land it in Delta, you get the Delta sharing. That hits your data supply chain much faster with better rigor and compliance. So it's a lot of things that you get out of Lakehouse. That's data in general. That's not geospecific. Today we're focusing a little bit more, but all of those remain in place.
And that's exciting with the announcements earlier this year about data marketplace, the Delta marketplace eventually coming out. That kind of data as a product. If people are thinking about that and thinking about getting those things in line, they're going to be in a great place when they can then start productizing it, monetizing it. being.
I would actually open that door a little bit more. So it's not just data as a product, is insight as a product.
Yeah.
Pretty much, it's just anything you can produce as a part of Lakehouse can be a product. So that could be your dashboard, that could be your data, that could be your model. It's a little bit broader than data. Data is one of the digital products. Maybe we can call it that way.
Very cool.
If we can go then to the next slide, which is the last thing I think we're going to cover here, which is the framework we mentioned, Mosaic. So far we focused a little bit on the native support and Photon. I said Mosaic uses Photon functionality under the hood, but it also provides you that hybrid outlook. So if you do have detail-centric use cases, you may actually need that hybrid. And we have packaged a lot of patterns for you in a neat thing that you just can pip install onto your notebooks, and off you go. And if we go to the next slide, the vision is that you go through your traditional steps of your medallion structure. Ingestion, we're talking bronze. Processing, it's a repetitive, maybe iterative process of going through multiple stages of your silver. Once you're ready, you can use it for ad hoc visualizing. As I said, for enterprise grade visualization, we probably need to think about what else needs to fit into your ecosystem. But those are the steps of very bird's eye view, but pretty much ingest your data, process it a few times, happy with it, and then service it. One thing that is coming soon into it is the raster support. So we're looking into integrating GDAL as a little bit more managed experience through Mosaic Lens. And
have you got details later about how people actually get hold of Mosaic and kind of the links to the GitHub repo and all that kind of stuff?
We'll provide all of those again in the description. There's going to be a very, I think, populated description, this one.
So we'll upload the links. It'll be fun.
A link to documentation, a few blogs there. And I think in the next couple of slides, we're actually going to talk why is this cool, because we have some use cases. And we'll provide the links to the videos or blogs describing those use cases as well.
All right. Well, okay. Well, do you want to tell us why it's cool then?
Yes. Next slide. That's finally all of this for something like this. So I kind of alluded on the flight holding patterns. So one of the, let's say, traditionally difficult use cases, because you need to think about the projection, you need to think about relation between the points. If you use something like H3 for abstraction, you can actually create a very easy to consume data asset for these kind of holding patterns, and you can actually count how often you revisit certain cells. Holding patterns are usually very repetitive in their sense because the planes are going around. So combining a little bit of domain knowledge with a bit of a H3 gets what's there, 7 lines of code, and you can get yourself an output that can detect something as complicated as a holding pattern. So this is available on our public documentation page. This is one of our starters for the product capabilities through Photon. So I do invite you to try it out. It's really cool. And actually, it gets really nice visualizations as well. So a nice one. Cool. Moving into more complicated, bigger volume, bigger scale. So we have recently announced a blog with Tezos. It's one of the startups in US handling geofencing and attribution to stores, and we've done an implementation using a combination of H3 and Mosaic in their use case, and we were the numbers speak for themselves. I'll let you consume it here, but this is where we first tried to handle petabyte level of data with these tools, and it's been doing its job more than well. So we're expecting up to 10x price performance improvements using these tools. So I do invite you to read out the whole blog. There is a lot of good stuff there, and walks you through caveats and principles and everything important.
That's very cool. And I guess from that quick diagram, we can see like a real close-up example of the Mosaic implementation, in that you've got the full H3 cells, and then you can see the chipped cells, kind of where it's gone and chopped them. Exactly. So it fits the actual shape.
It gives you that ability, duality, so you can decide whether to take it into account or not take it into account.
Yeah.
It's really quick. It's just a filter. So having that flexibility is really important. Is just we're not boxing you into anything. We represent your data in a way you can consume it best, and then allow you to choose your path.
Cool. Very cool.
And the final one, which is the sheets. There is a video of them walking through this use case as a part of the keynote for the Spatial Data Science conference that was held in New York a couple of months ago. And I think the only thing that I would reiterate here is performance is pretty good here. We're talking about going from 2 hours to 7 minutes. I mean, that in itself, it's a statement. So again, I would invite you to do check the video. It walks you through the whole implementation. But basically, in this particular use case, they were comfortable with the deluge of details. So this is more H3 centric rather than the hybrid. So you get both parts of the path. And they really got the maximum when it comes to the simplicity of SQL, but speed of Photon.
Very cool. So I guess there's a few different kind of types of people that kind of should be interested in this, right? There's people who are currently doing geospatial but just struggling with speed and having to maybe limit the amount that they do it over because it doesn't perform that well, or they only refresh it every so often because it takes ages and ages and ages to process. Whereas if they're looking to adopt this, it should scale better. And again, if they can achieve that kind of 2 hours to 7 minutes, they can just afford to do more and do it more often or do more of it. So there's lots of people who are currently doing it who could probably benefit. And then people who have never thought about it and thought it was too complex, too hard, too tricky to get started with.
Well, I mean, I'm going to throw also an interesting philosophical thing into the mix as well. Performance is a sustainability problem.
Yeah.
If you spend less compute on solving the problem, you're actually reducing your CO2 impact. So it's not just about the dollar amount. It's also about what we're doing for, because we're using data to solve the real problem, so to make the society better. But we don't really need to run things for hours and days if we can run it faster. So scalability is an interesting problem from a broader perspective as well.
Yeah, makes a lot of sense, and it's a good angle. It's a refreshing angle from the Spark world where we used to fairly brute forcing a lot of things. It's good to stop pulling that back and going, maybe let's be a little bit more judicious with how much compute we're using. It's fair.
I kind of like when I hear, we can do it in a minute, we can do it in a second kind of thing. I'm one of those guys. I don't like, lengthy processes. So,
that's fair. I don't think anyone does. Cool. Is there any more slides? Are we on the last slide?
I believe we have concluded. We wanted to finish it with a nice thought on a use case. I think that's
cool. So let me just switch us into a quick wrap up. So what should people do after seeing that? Kind of what next action should people take?
Well, so first of all, they can reach out to myself. We'll provide a link to the LinkedIn. So I'll be more than happy to talk about anything geo with you or anything data, pretty much. I have a few other hobbies data-wise as well, and we'll provide links for the Mosaic landing page with documentation. So please visit it, and the links for the use cases that we have covered. So those are a couple of blogs, the H3 product documentation. As I said, it's going to be a lengthy list, but there is I think something for everyone. So
that's very cool. So then in follow-up videos, so I promised that I will go and have a go with one of the solution accelerators and do a video just walking through, getting started. As someone who doesn't use this stuff a lot, I'll just see how easy it is to pick up and get started and get things working. But are you happy to come back for a future video to go dive into a little bit more depth and take us through an example and talk a bit more about the actual code under the hood?
Yes, absolutely. So I'm more than happy to do another video soon, and we can cover some more advanced use cases and more details on how we went about it, which principles we used, and how grid index system helped us there.
Awesome. Well, thanks very much for being on the show, and I'll just do a quick wrap up. Alrighty. So we've seen a lot of information there after introducing a few new concepts. If you hadn't really seen H3 before, and you hadn't heard of Mosaic, the Databricks Labs project actually sort of uses it and gives you a load of more additional functionality out of the box. There's a ton of stuff to go and look into. As promised, we'll put lots of things in the description down below, some links to the blogs, links to the projects, things you can go and check out. So if you are getting started with geospatial, if you've got any geospatial problems, if you want to know how you would apply this to a particular problem, just let us know down in the comments and I'll pass it on, and then we'll see what we can get to. And again, so more videos we can do on this topic to do more stuff. And as always, don't forget to like and subscribe, and I'll catch you next time.